In this video, we'll take a look at orthogonal matrices. Here's our problem. We're told that A and B are orthogonal matrices, and we're supposed to show that the matrix BA is also orthogonal. Let's make sure we're familiar with the definition of an orthogonal matrix. An orthogonal matrix is a square matrix whose columns form an orthonormal set. So there are really two conditions here. First of all, the columns must be orthogonal to one another, meaning the dot product of two different columns must be 0. And secondly, there's this normality condition which tells us that each column vector must have length 1. So here's an example of an orthogonal matrix. If we look at the column vectors here, they are orthogonal to one another. And each vector, the first column and the second column, each vector has length 1. This definition up here is what's considered the formal definition of an orthogonal matrix. But what we need is an algebraic way of expressing the fact that a matrix is orthogonal. So we're going to use the fact that a matrix Q is orthogonal if and only if Q transpose times Q is equal to the identity matrix. So going back to our problem here, we're told that A and B are orthogonal matrices. We want to show that the matrix BA is orthogonal. So using this version of orthogonality here, what we really want to show is that this matrix BA is playing the role of Q. So we want to show that BA transpose times BA is equal to the identity matrix. So let's get on to our proof. We are going to start with the left side of this expression here, BA transpose times BA, and step by step we are going to transform this into the identity matrix. If we can do that, then we're done the problem. So as a first step, let's use the property of the transpose of a product. Each of these factors here is going to transpose and the order is going to reverse as well. So we're going to get A transpose, B transpose. I'm just going to drop the brackets here and write down BA. So that is our first step there. We've just used that property of transpose of a product. Now remember that A and B are both orthogonal matrices. So this B transpose B is guaranteed to be the identity matrix. That is because B is orthogonal. Next we can say, well, identity matrix times any matrix just gives us back that original matrix. So we've really got A transpose A. And next we can use the fact that A is an orthogonal matrix, meaning A transpose times A is equal to the identity matrix. So we have, step by step, transformed our original matrix here into the identity matrix. That tells us that the matrix BA is orthogonal.